Hello guys. Good morning to all of you. Today in this session, we are going to talk about polarization. In one lecture, we'll try to cover the entire polarization. This is going to be a little bit lengthy lecture, but in one lecture, we'll try to cover everything from polarization. This is one of the most important topics from electromagnetic theory, and this is the part of our top 100 most important topics for the upcoming CSIR-NET exam. If you want to get enrolled in this top 100 most important topics course, you can enroll for it. The link is given in the description, and currently a special offer is going on, so you can get it at a very affordable price. So do check out the link given in the description. Okay, before I start, let me know if everything is all right so that we can start. Can you hear me properly? Look, what is polarization? Polarization is a property applying to a transverse waves. Okay, I think everything is all right. Let's start. Okay, so polarization is a property belongs to transverse wave. Transverse wave means, we have already told you, electric and magnetic field acts in a perpendicular direction, and the wave propagates in the direction perpendicular to both E and B. This is the property of transverse waves. So polarization is a property applying to transverse wave that specifies the geometrical orientation of the oscillation. In a transverse wave, the direction of the oscillation is perpendicular to the direction of the motion of the wave, and we have seen it. Electric field oscillates along this direction, magnetic field oscillates along this direction, and your overall wave is moving along the direction perpendicular to both electric and magnetic field. Light or any other electromagnetic radiation from any source, such as it may be from the sun, from the flames, incandescent lamps, it consists of short wave trains with an equal mixture of polarization. This kind of light is called unpolarized light. Like whatever light we are getting from the sun, you're burning something, you're getting light. So this kind of light sources will be called as unpolarized light. So they have a mixture of the oscillation in all the directions. Polarized light, on the other hand, it can be produced from the unpolarized light by passing it through a polarizer. So what is the job of a polarizer? The polarizer basically polarized the unpolarized light. Means in unpolarized light, we have the oscillation in all directions. The polarizer, what it does, it only allows one type of oscillations, and it does discard the others and make it a polarized light, which allows waves of only one polarization, as I told you, to pass through. The most common optical material, such as glass, are isotropic. Means in whichever direction you send the light in glass, they will move with the same velocity. So glass is an isotropic solid, and it do not affect the polarization of light. If you send unpolarized light after passing through the glass, it will remain unpolarized. So it does not change the state of polarization of the light. However, there exists some material which exhibit birefringence. Birefringence, dichroism, and optical activity. We'll talk about this thing later on. Look, whenever we talk about glass or water or some substance, they have one particular refractive index throughout the material. But for this birefracting crystals, which exhibit this birefringence phenomena, they have two refractive indices. Okay, bi means two, refringence means it will have two refractive indices. We'll talk about it. And this kind of material can change polarization of light. It can it can make the unpolarized light to a polarized light. Some of these examples may be some of these are used to make polarizing filter. Light is also partially polarized when it reflects from a surface. We have already talked about it. You know, if light incident on a surface, it gets partially polarized. In this picture, the scenario has been portrayed very clearly. As you can see, we have sent an unpolarized light. Unpolarized light means it doesn't have any fixed orientation, a fixed direction of oscillation. You can see the oscillating along this. So it's randomly oscillating. Now you have passed it through a linear polarizer, which has a pass axis along this direction. So you can see only the oscillation which is happening along this direction will get passed through, but this kind of oscillations which are making some angle, they will be cut off. Okay, this will pass through. As you can see, after passing through a linear polarizer, it becomes a linearly polarized light, and it has a fixed direction of oscillation. It is oscillating in a same plane. Now, if you pass it through quarter wave plate, so we'll talk about this quarter wave plate, half wave plate and all. Quarter wave plate, if it a linear polarized light pass through, it makes it left-handed circularly polarized light. Left-handed circularly polarized means you can see the oscillation. So it is oscillating in the form of a circle, but it is left-handed, means it is orienting and the direction opposite to the direction of the clock. The clock moves along this direction. Okay, left-handed means anti-clockwise. So you can see moving in an anti-clockwise direction. So this quarter wave plate basically turns from linearly polarized light to a left-handed circularly polarized light. Good morning, Murli. Where is Harry today? Hari Ajay. Okay, in this picture, we have tried to show the electromagnetic wave and its transverse nature. As I told you, electric field, we have already talked about it. This is the oscillation of electric field, and this is the oscillation of magnetic field. And you know, this k is the wave vector. It denotes the direction of wave propagation, and s also denotes the direction of wave propagation. Like the direction of s is the same as the direction of k, because s is a pointing vector. Pointing vector is given by the cross product of e and h. And that is why you get a direction perpendicular to both e and h. So these pictures are very important. And in this picture, it has shown that this lambda, you know, the peak to peak distance. So this is how the electromagnetic wave propagates. Electric field, magnetic field, electric field, magnetic. Now, in general, in electromagnetic wave, electric field dominates. As you can see in this picture also, this magnetic field is feeble, electric field is more. That is why whenever we represent electromagnetic wave, we generally represent by E. Okay? Generally, we represent by the electric field. So, to represent electromagnetic wave, we represent it by stating its electric field. Now, here some example has been shown. You can see if the pass axis, okay, this is your pass axis. Pass axis means the axis through which the oscillations are allowed to pass. And you can see the oscillation is making an angle theta with the pass axis. Then you can see the component which will come through it will be the theta component, along the path direction. So component of this E along the path axis. So if this is theta, this is E cos theta. So E cos theta will come out. So these are the overall view of the state of polarization. Amplitude of the electric field is greater than the magnetic field. Yes, way greater than the magnetic field. That is why we represent the electromagnetic wave mainly by the electric field, because you know relation, right? B naught is equals to E naught by C. You can imagine it is scaled down to C, it is divided by C. So you can imagine how small this P naught is. Now what is plane of incidence? Incident ray, reflected refracted ray and normal to the incident forms a plane that is a plane of incidence. So you can imagine it in this way. There is interface, incident ray, refracted ray, reflected ray, they are all forming a plane. This plane is known as the plane of incidence. If this is theta, this will be theta, and this will be some, let's say, phi, angle of refraction. Now you can produce plane polarized light or linearly polarized light. Plane and linearly will take to be equivalent. Different methods of production of polarized light are: number one, polarization by reflection. As I told you, polarized light can also be produced from the reflection. Polarization by refraction, polarization by selective absorption, polarization by double refraction, and polarization by scattering. Out of these, we'll talk about mainly this polarization by refraction, double diffraction, and reflection. So mainly these three will be discussed. Now let's talk about the first one, polarization by reflection. So what happens, let's say you have a linearly polarized light. Look, let me tell you one thing. If you want to show the polarization of an electromagnetic wave, in electromagnetic wave what we have electric field and magnetic field direction. So if this you want to represent an unpolarized light, unpolarized electromagnetic wave. In electromagnetic wave we have electric field and magnetic field. They are oscillating in a perpendicular direction. So we can show it in this way. Okay, this is the oscillation of maybe electric field or magnetic field, whatever you say, and its perpendicular oscillation is represented by this. So if you see both, this dot shows perpendicular and this line shows parallel, it means it is unpolarized. Okay, now if you just exclude or cut off one of the components, let's say you just exclude the vertical component, perpendicular component, this is unpolarized. Let's say you have used some polarizer, it will become a polarized light. So let's say after passing through a polarizer it becomes like this. So you see the one component of the oscillation has been removed. So this is then polarized. Okay. So let's say we have an interface of two medium like this. A linearly polarized, plane polarized light is incident at some angle, let's say theta. So it will be refracted and reflected. So let's say this angle is theta p. This is n1, this is n2. So if this happens, there will be no reflection. Theta p is called the polarizing angle. Linearly polarized light, we are taking a plane polarized, so it will look like this. Only one thing will be there, like this. And it will become like this. Look, if a linearly polarized light from the polarizer, it contains any one of the field or E or M. Yeah, that is what I showed. Polarizer, if depending on the path axis, it will have the components. Okay. So if you have a polarizer which has a path axis, let's say in this way, you have a polarizer in this way, and it has a path axis like this, then what will happen? This component, the red one will pass through and this blue one will be blocked. On the other hand, if you have a path axis, let's say along this, what will happen? The blue one will pass, red one will be blocked. Okay. Look, if a linearly polarized light look here, electric field vector, this shows the direction of E. Okay, electric field vector associated with, not direction, actually oscillation, associated with the incident wave lies in the plane of incidence. You know, this is the plane of incidence. This overall plane is the plane of incidence, where we have the reflected, refracted, and perpendicular to the interface lies in the plane of incidence. If a linear polarized light is incident on the interface of two dielectrics with the angle of incidence equal to theta. Okay. Now, if the angle becomes theta p, so you can incident it at any angle for a set of n1 and n2. n1 and n2 are what? The refractive indices of the two media. So if you choose the angle, if the angle of incidence theta is such that theta is equals to theta p. If you somehow can make it tan inverse the ratio of their refractive index, then the reflected light will be completely off. Then the reflection coefficient is 0. So what does it mean? If you, let's say, incident at some other angle, what will happen? You will get your refracted ray as well as reflected ray. Now if you keep on changing the theta and if you incident it at theta p, there will be no reflection, only refraction will be there. So this angle is called polarizing angle. So this is the case of linearly polarized. What will happen to an unpolarized light? Instead of this linearly polarized, if you have an unpolarized light, what will happen to this picture? Let's say you take an air glass interface. Now we have unpolarized light means what? This is a light wave. This is the electric field oscillation. It shows the electric field oscillations. We want to make it unpolarized. It means we'll also have to show the oscillation of the magnetic field. So this becomes unpolarized light. And if you incident it at an angle, let's say theta p, what will happen? For unpolarized light, there will be reflected ray as well as refracted ray. Okay. This angle will be 90 degree. Remember. So you can see the vibration here for this reflected ray, and for refracted ray the vibration will be like this. So previously it was unpolarized. After reflection it becomes plane polarized or linearly polarized, and this is partially polarized. Okay. So you see, if an unpolarized light is incident with an angle of incidence let's say equal to theta p, the reflected light is plane polarized. So this equation is known as Brewster's law. This is known as Brewster's law. So Brewster's law states that if you make the incident angle of incidence equals to tan inverse of the ratio of the refractive indices of the two medium, then an unpolarized light will become polarized. This theta p is known as the polarizing angle. From the polarizer, it contains any one of the, okay. Why we call reflection light is plane polarized and refracted light is partially polarized? Yeah, actually both are polarized, right? This is happening, the oscillation is happening at a particular plane. We are calling it plane polarized. So it may be different, the polarization will be, it may be different. Okay, it is partially polarized, it may be, there may be elliptical polarization and many other type of polarization. We'll solve some problem, you will see why we are calling it partially polarized. It is confirmed that it is plane polarized. The reflected light will be plane polarized. So there is not only plane polarized, there may be circular polarization, elliptical polarization and all. That is why we have not mentioned which kind of polarization it is. It will get polarized, but the state of polarization is not known. Okay. Hanumantaru for CSIR coaching, which amount can I pay? You can visit our website www.physicshub.in and you can check the courses, or you can also download our physics application from the Play Store, and from there also you can sign up and check and you can purchase it. As far I remember, now currently offer is going on, so you will get it at maybe 6499 or something. Okay, so when you send this unpolarized light at an angle theta p, you see the reflected and refracted light, they will make 90 degree with each other. At the polarizing angle, what happens? The reflected and the refracted rays are at right angle to each other. So if you consider this angle to be theta p, angle of refraction will be, let's say, r, right? So we can say theta p plus r. Okay, look, from the law of reflection, law of reflection, what does it say? That angle of incidence will be equals to angle of reflection. So this angle must be theta p, and as you can see, this total angle is pi and this angle is 90 degrees. So obviously theta p plus r will be 90 degree, है ना? Theta p plus r is equals to pi by 2. Now you see, tan inverse n2 by n1 is equals to theta p. Now if I consider the air glass interface, what is the value of n1 here? N1 is equals to 1, and what is the value of n2 here? N2 is equals to, let's say, n 1.5. For glass it is 1.5, so we are calling it n. So for this particular set, you know, tan inverse theta p is equals to, okay, for this particular case here, tan inverse n2 by n1, so n by 1 is equals to theta p. Okay, we can say n is equals to tan theta p, that is equals to sin theta p divided by cos theta p. This is equals to sin theta p by cos of theta p. Theta p is pi by 2 minus r. So this is sin theta p divided by sin r. Okay, or we have just done the reverse thing actually. Acha. Okay, this is one thing we can do. Another thing we can do. Okay, let's not go in this way. We are basically trying to prove the Bistar's law, right? So what we will do, we will go from the Snell's law, right? What is Snell's law? N1 sin theta 1 is equals to N2 sin theta 2. So N1 here, look, N1 sin theta 1 is equals to N2 sin theta 2. What is this law called? This is law known as Snell's law, right? Am I right? Now, N1 is equals to 1 here. So 1 into sin theta 1 is theta p, N2 is equals to N, sin theta 2 is equals to sin r. So N is equals to, you see, sin theta p by sin r. That is N is equals to sin theta p divided by sin pi by 2 minus theta p. So this becomes cos theta p. Sin theta p by cos theta p is equals to tan theta p. Okay. So theta p is equals to tan inverse n. So we got it back, the Bistar's law. If I consider the air glass interface, for the air glass interface, N1 is equals to 1 and N2 is equals to approximately 1.5. So this gives you theta p, which is tan inverse 1.5, approximately 57 degree. So in this particular case, if you incident this unpolarized light at angle of 57 degree, you will get this plane polarized light and partially polarized light, refracted light. Clear? Any question from it till now? Tell me, guys. Can you go for a problem? Okay, look at the problem. Came in December 2015. A beam of unpolarized light in a medium with dielectric constant E1 is reflected from a plane interface formed with another medium dielectric constant E2. So you know a relation between the refractive index n and the dielectric constant is square root of E epsilon. Na? Epsilon is the dielectric constant, n is the refractive index. The two media have identical magnetic permeability. That is why we could write it this. If the angle of incidence is 60 degree, then the reflected light. Okay, here you add one line. This is plane polarized light and the direction of polarization is the perpendicular to the plane of incidence. Plane polarized light bracket में perpendicular to plane of incidence. Polarized perpendicular to the plane of incidence. So this dot shows it is perpendicular to the plane of incidence. Which option will be correct? We have to check this angle of incidence if it is equal to the polarizing angle. So what is the check? The check is we need to find out, we need to match it with the Brewster's law. This angle is given to you as 60 degree and you are sending an unpolarized beam. So it will have both type of vibrations. Now epsilon 1, so n1 is equals to root over epsilon 1. Here n2 is equals to root over 3 times epsilon 1. Theta p was what? Tan inverse n2 by n1. So let's evaluate if it is matching with that. Tan inverse n2 by n1. So how much it is? Tan inverse n2 is equals to root 3 root over epsilon 1 divided by root over epsilon 1. So tan inverse root 3 is equals to 60 degree. Okay. So this is the angle of incidence and this is the polarizing angle. This polarizing angle is equal to the 60 degree. So we know for that kind of case it is plane polarized perpendicular to the plane of incidence. Reflected light will be plane polarized perpendicular to the plane of incidence. Is it clear? So the reflected light will show oscillations like this. Look at this problem. A circularly polarized monochromatic plane wave is incident on a dielectric interface at Brewster angle. Which one of the following statements is correct? Now instead of unpolarized light, you have incident circularly polarized light. Look for circularly polarized light. We can decompose it into two perpendicular components. One is along the plane of incidence, another is along the perpendicular to the plane of incidence. Okay, let's check that figure. Reflected light is plane polarized in the plane of incidence, and the transmitted light is circularly polarized. Reflected light is plane polarized perpendicular to the plane of incidence. Transmitted light is plane polarized in the plane of incidence. Reflected light is plane polarized perpendicular to the plane of incidence, and the transmitted light is elliptically polarized. There will be no reflected light. Transmitted light is circularly polarized. Which one option is correct? So option D will not be correct, as you can see, because it is incident at a Brewster angle. So the reflected light must be plane polarized light perpendicular to the plane of incidence. This one is true. What about the transmitted light? As I told you, transmitted light will be partially polarized. So if circular polarized light we have, what should be the transmitted light according to you? Look, if it were only circular polarized light and it is incident on some surface, what does it mean? It means it is changing the medium, right? It is changing the medium. Light is changing the medium when it is entering into some other, let's say, medium. When it is changing the medium, obviously it will not remain in its original state. So if you had circular polarized light and it is incident or a Brewster triangle, so the reflected light will be plane polarized, and what should be the refracted or transmitted light as per you? B. And the transmitted light is plane polarized in the plane of incidence. Will it be plane polarized? Because you have not sent unpolarized, you have sent circularly polarized light. Okay. So you can imagine it in this way. You have this circularly polarized light. So after transmission, what should it become? From circle to which shape it may become? Should it be like this, or from circle it will be taking a form of an ellipse? Which one is more logical? See, na? From circle it will become ellipse. The reflected light is plane polarized perpendicular to the plane of incidence, and the transmitted light is elliptically polarized. Okay, you can just write one explanation for this. So circularly polarized light can be decomposed into two perpendicular components, one in the plane of incidence and the other perpendicular to the plane, perpendicular to it. What happens at a Brewster's angle? At Brewster's angle, the reflected light contains only perpendicular component, and the refracted light has larger component in the plane of incidence than its component perpendicular to the plane. Thus, it will be elliptically polarized. Okay. I hope this is understood. Let's go for Malu's law. What does it say? Let's say we have an unpolarized light and it is moving in a direction like this. If you want to denote the unpolarized light, how will you denote? We'll denote it by this. The larger component in the plane of incidence than this. So it's like this. Larger component in the plane of incidence than its perpendicular component. So it will become an ellipse. Previously it was like this, circle, then it becomes ellipse. So you understand how can I draw it. Clear? आगे बढ़े. Okay, look at this Malu's law. So what does Malu's law state? Okay, you see, we are sending an unpolarized light. Unpolarized light means it will have its oscillation along all the directions in random directions. Okay, so this shows unpolarized light. Now, if this unpolarized light passes through a polarizer whose path axis is along, let's say, x axis, this is your z axis. Now perpendicular to this we will have our x axis. This is the path axis. So let's say you have placed polarizer along this direction. What will happen? Let's say it is made to pass through a polarizer. Let's say this P1. what will happen? Only this component will pass through. Okay. So from unpolarized light, after passing through a polarizer, it becomes a polarized light, linearly polarized light or plane polarized light. Now, if you pass it through another polarizer, which is making an angle, let's say some angle. Look, this was the x direction. Let's draw that x direction first. This was the pass axis of this polarizer P1. So we are now including another polarizer which is making an angle, let's say theta. Then how the intensity will change? Look at it. The oscillation is slightly reduced from unpolarized to polarized. Now what will happen if I pass it through another polarizer whose pass axis is making an angle, let's say theta with x axis. This is the angle, now it is theta. This is another polarizer P2. What will happen? The intensity, only this component will pass through. So it will be having less intensity. Okay. So a cos theta component will pass through. This is given in Malus law. To highlight the change, we are just making it a little bit. Look what is happening here. An unpolarized light beam gets polarized after passing through the polaroid P1, which has a pass axis parallel to the x axis. Okay, this is the pass axis. Now, after passing through polarizer P1, when this x polarized light is incident on the second polarizer, P2, whose pass axis is making an angle, let's say theta, with the x axis. Then what will happen? Then the intensity of the emerging light, it will remain polarized, okay, will vary as I equals to I naught cos square theta. Is not completely blocked when the path axis makes an angle with x axis. No. It is not completely blocked. Its intensity gets this cos theta component. How intensity varies? I is equals to I naught cos square theta. In this way, the intensity is varied. You can imagine, should it get completely blocked? Murli, just think it practically. If some light is coming, okay, if it gets a straight opening, it will pass through. Now, if you make the opening, let's say with an angle, it will not go that much, but it will go. Na? You will get the intensity on the other side. So this is practically, you think you will understand. So it will get reduced, but how much it will pass through? So you must have seen in some videos or in some reel that people take two sheets of polarizer, and when they keep it parallel to each other, you can see through it. Now as you keep on rotating, at some particular angle it will become 0. So if you want to completely block it, you have to make it perpendicular to this. If you make this optic axis perpendicular to it, it will get completely blocked. Okay, so you see cos 90 is equals to 0, the intensity will be 0. So that is why you have seen people that they took two polarizing filters and they keep it like this, and once they start rotating, and at one position you see it is completely black. What is happening at that position? It is becoming perpendicular, cos 90. If this theta becomes like this, so it will be perpendicular. Now you see, for this unpolarized light, can we specify theta? Can we specify theta? For unpolarized light, theta is randomly oriented. You see the direction of oscillation is random. So here you have to take an average value. Okay, na? Average value of cos square theta. So this is the mathematical form of Malu's law. I is equals to I naught cos square theta. Now what you can do, we can do this thing. Let's say you have a linearly polarized light in incidence on some polarizer, and you can rotate the polarizer, and you will see a variation of the intensity, and that is used in polarimeter. If you have done the practical with polarimeter, we had polarimeter practical in our university. X instead of y axis, if we put a polarizer, it will be completely blocked. No, from the unpolarized light it will not get completely blocked. After this P1, if you keep a polarizer along the y axis, the path axis, if it along the y axis, then it will be completely blocked as per this law, and so overall. Okay, let's say this is your linearly polarized light. Now we have a path axis. which is making an angle. This is theta. If this intensity is I naught, after emergence it will become I naught cos square theta. Okay, and that means this is I naught. Let's say instead of this, if you make it perpendicular to it, so this will be 0. So there will be no light. Here it is partial block, we can say. Okay, one problem came like this in December 2011. Do it. Look, consider three polarizers P1, P2, P3 are placed along the axis. Unpolarized light I1, I naught. So what will be the next light? You see, unpolarized light means it has various components. It has random oscillations. It can oscillate in this direction, in this direction, in this direction, in this direction. So here, when you calculate after passing through a polarizer, you know how it varies. It varies at I naught cos square theta. So as theta is random, we need to take the average of this cos square theta. So it becomes I naught cos square theta average. So that is why it becomes I naught by 2. So after passing this unpolarized through a polarizer, it becomes a polarized light of intensity I naught by 2, and you can see it will emerge as a component like this. So this is the pass axis, so it will be like this. Now you do the remaining thing. Look, this theta is the angle which is making with the previous pass axis. Okay, previously the pass axis was along x direction, so the next pass axis, whatever angle it is making with the previous pass axis, that is theta. Do it. Tell me the answer. Look, this becomes I naught by 2. Now it is making an angle theta, so the next polarizing light will be like this, somewhat like this. So initially here I naught is I naught by 2 cos square theta, right? Now again it is passing through this. So previously you see the direction was this. This was the previous direction. And this is the new direction. So what should be the angle? this angle should be taken now, है ना? So you see, if this angle is theta, what will be this angle? This angle is theta. This angle is theta. So obviously this will be 90 degree minus theta. Now we need to consider, after passing through this, okay, we have just messed out. We have just messed it. Let's change the color. This is the pass axis given to you. So original intensity for this case is I naught by 2 cos square theta. Now how much portion it is? Cos square nu theta. Nu theta is 90 degree minus theta. Okay, this will be the answer. So you can see it is I naught by 2 cos square theta. Cos 90 degree minus theta is sin theta. It becomes sin square theta. So 2 cos theta sin theta is sin 2 theta. No? So you have to multiply by 4 divided by 4. So it becomes I naught by 2 into 4, 8 sin square 2 theta. Acha. Option C is matching. Na? Tell me if anyone has any doubt. Clear? Harry, Mulli? Okay, let's move on. Now, from the different components of polarization, from the different oscillation component of polarization, we can define different state of polarization. Let's say we divide the polarization into two components. One may be, there may be X component and there may be Y component. So they are oscillating. So mathematical. So one component is varying as, let's say, A sin omega t plus delta. Another component is varying as B sin omega t. Okay. So what we can write, x by A is equals to sin omega t plus delta. So this is sin A cos B plus cos A sin B formula. On the other hand, y by B, if I write, we can write it as sin omega t. So if you square and add them, what you will get, x square by A square, let's say, plus y square by B square. You will get how much? If you want to calculate this, we need to, you can say sin omega t is y by b. So we can just express it. Let's say x by a is equals to sine omega t is y by b. So y by b cos delta plus cos omega t. Sine omega t is y by b, cos omega t is 1 minus y square by b square square root sine delta. We can write it in this way. Therefore, x by a minus y by b, let's say cos delta, is equals to 1 minus y square by b square square root into sine delta. So let's say square. So square root becomes 1. So it becomes like this. So what will become x square plus a square, x square by a square plus y square by b square. So let's break it up. X square by a square plus y square by b square cos square delta minus 2xy by ab cos delta is equals to sine square delta minus y square by b square sine square delta. So y square by b square cos square delta plus y square by b square sine square delta, it becomes x square by a square plus y square by b square minus 2xy by ab cos delta is equals to sine square delta. Can you write it? Now let's take different cases. We'll solve a problem later on, then you will understand it more clearly. For the timing, you know that this is the x component, this is the y component. Just look at this calculation. Let's say when the phase difference delta is equals to 0, 2 pi, 4 pi and so on. In short, when delta is equals to 2m pi, then what will happen? Cos 2 pi cos 0 is 1 and the right hand side is 0. So we have x by a minus y by b whole square equals to 0. Okay, so from this we can say that y by b is equals to x by a, or y is equals to b by a times x. What does it represent? It represents a plane polarized light. This is the first case. Let's take another case, case 2. Let's say when your delta is equals to pi, 3 pi, 5 pi and so on. That is odd multiple. 2m plus 1 pi. So obviously this cos delta will be minus 1 and sin square delta is 0. So it will become x by a plus y by b whole square equals to 0. Achha, this will be your plane polarized. So here y is equals to minus b by a into x. So it is also plane polarized. But it is making an angle minus theta with x axis. So it is making an angle plus theta with x axis. Here it will make minus theta. So this is y equals to mx formula, straight line. This is y equals to minus mx. So what change we can get for the second picture? So previously this was the case. Now what will happen? It will give you like this. Y equals to minus x. This angle is theta. Previously we had this. Let's take another case, case 3. When let's say delta, what is delta? Delta is the phase difference between the two components. You see, one component x, another component y. So along x axis you can see we have shown you the y, along y axis it is b. Delta is the phase difference between these two components. So when delta is half integral of pi, it may be pi by 2, 3 pi by 2, 5 pi by 2 and so on. So you can see this cross term will be 0. In that situation, what will it become? X square by a square plus y square by b square minus 0 is equals to sin square delta. Sin square delta and sin square pi by 2, that is 1. 3 pi by 2, 5 pi by 2 square is there, so it will always produce plus 1. So what kind of light it is producing? If two light waves are superimposing, so what kind of light wave it is producing? This is elliptically polarized. Now you can take a fourth case. Let's say when delta is equals to m plus half pi and a equals to b, then what will happen? If you put a equals to b, it will become x square plus y square is equals to a square. So the emergent light will be circularly polarized. Understood? Now this is clear. Anyone has any doubt? Let us solve a problem to understand it better. So this kind of problem you can expect from this particular topic. The electric field of an electromagnetic wave is given by this E naught cos z omega t. This is the x component, right? Ex or x. This is the y component. This represents what kind of polarizing state it is. From kz plus omega t, you can see it is moving along negative z direction. As I have told you, if you see in the argument, let's say cos or sine, whatever it is, kz minus omega t means the wave is moving. The wave is moving, say, in z cap direction. Now if you see this cos kz minus omega t, and if you see, let's say cos kz plus omega t, it means the wave is moving in the negative z cap direction. So here it has plus, so wave is traveling in the negative z direction, so positive wala hum log can cross. So option will be between B and C, whether it is circularly polarized or elliptically polarized. C, an elliptically polarized wave traveling in the negative direction. M value for circular, M value you can see m plus half pi. M is as usual 0, 1, 2, 3. Same condition of the elliptical, only when the oscillation amplitude will be same, then it will become circularly polarized. Option C, clear? So you can see Ex here, Ex is equals to E naught cos kz plus omega t, Ey 2 E naught sin kz plus omega t. Now to compare, what you can do, you can write it in this way, cos kz plus omega t. If I write it as minus pi by 2 plus pi by 2, let's say, right? So cos this plus cos pi by 2 plus theta is equals to minus sin theta, so a minus sin will be added. So we can say that Ex by E0 whole square plus Ey by 2E0 whole square, it will be cos square kz plus omega t plus sin square kz plus omega t, that is 1. So from here also you can say it is elliptically polarized. Because E naught and 2 E naught, and from this also you can make this argument, delta is equals to m plus half times pi. So here as you can see, what is the delta value? Delta is equals to pi by 2 here, right? And A not equals to B. That is why it is elliptically polarized. Clear? Any question comes from this topic, you will be able to do. Okay, let's move forward to another problem. Do this one, simple one. The state of polarization of light with electric field vector E is equals to this is, क्या होगा? Ex is what here? E naught cos kz minus omega t. You imagine Ex is the x which we have discussed in the previous topic. Ey is like y which we have discussed in the previous topic. Ey is equals to how much? Minus E naught cos kz minus omega t. So obviously this is minus Ex now. That means Ey, Ey is equals to minus Ex. So which case it is? I think it is case B, na? Case 2 we discussed. Yes, it is like the case 2 where B by A is equals to B is equals to A. So how will it look like? It will be like this. This angle is theta. What will be this theta? Minus 1. You see, M is equals to minus 1. So Y is equals to mx. If M becomes minus 1, what does it mean? Tan theta is equals to minus 1. So theta is equals to minus 45 degree, right? So that is why it is the negative 45. And this shows linearly polarized, plane polarized. Which option you are getting? Linearly polarized at minus 45 degree angle to x axis. Option B, na? Let me know if it is done. Harry Murli. Let's go for another problem. Unpolarized light falls from air to planar air glass interface. Refractive index of glass is 1.5 and the reflected light is observed to be plane polarized. The polarization vector and the angle of incidence theta I are. A, B, C, D, which option is correct? Reflected light is plane polarized. It means what? The angle of incidence must be equal to the polarizing angle. Since the reflected light is observed to be plane polarized, the angle of incidence theta I must be equals to the polarizing angle theta p, and theta p, you know, tan inverse n2 by n1. So here air glass interface, so n2 is equals to 1.5, n1 is equals to 1. So tan inverse 1.5, and you know the value of tan inverse 1.5, it is 56 degree. Right? The polarization vector and the angle of incidence theta I are perpendicular to the plane of incidence, and theta is equals to 56 degree. See. चलो आगे बढ़ते हैं. Do this one. The electric field of an electromagnetic wave is given by E is equals to 3 sin kz minus omega t x square plus 4 cos kz minus omega. The wave is. Can you do this problem? Two components are given to you. Okay, the first part is quite easy. Second part, is it in the clockwise direction or in the anti-clockwise direction? That we need to figure out. You see, here the electric field of the electromagnetic wave is given by, so Ex is equals to 3 sin kz minus omega t. We can write Ex is equals to 3 sin kz minus omega t. And what about Ey? Ey is equals to 4 cos kz minus omega t. Am I right? Yes, absolutely. So to equate it, we need to express this it in the form of sine. So sine kz minus omega t plus pi by 2. So sine in the second quadrant is positive, so that we don't need to add a negative sign here. Okay. So as you can see, they have a phase difference, delta is equals to pi by 2, and A is not equals to B. Obviously this is electrically polarized, therefore it represents an elliptically polarized light. Now the question about the direction. Okay. So let's say, to understand this, what we are doing, let us try to understand its behavior. Initially, okay, this is x component, this is y component. Initially, it is here. How it is here? Let's say this is x, this is y. Z axis is perpendicular to it, right? So we can consider that at z is equals to 0. So at z is equals to 0, what will be your ex? If you put z equals to 0, ex will become minus 3 sine omega t. And what about ey? Ey will become cos of minus theta is plus cos theta, so this is 4 cos omega t. No issue till now. Now it is varying as omega t. So let's say we are considering omega t is equals to 0. See, this is the initial time. At omega t equals to 0, you can see ex is equals to 0, ey is equals to 4, 0, 4. So this is the initial state, right? Now at some later time, omega t is equals to, let's say, pi by 2. So you can see t is equals to 0 here, t is equals to pi by 2 omega, you can say. So at t is equals to pi by 2, our ex will become minus 3 into pi by 2, that is how much? Minus 3. Ey, how much? Cos is 0. So previously it had 0, 4. Now it becomes minus 3, 0, means here it is finally coming to this. So which direction it is moving? Previously it was oriented along this direction, and now it has come to this. So what is this direction? Obviously this is anti-clockwise. Okay. Therefore, the wave is elliptically polarized in counter clockwise direction when seen traveling towards the observer. So instead of this minus 30, if you would have got plus 30, then we could say that it was moving in the clockwise direction, clockwise sense. So this is option D. Any question, guys? Elliptically polarized in counterclockwise direction when seen traveling towards the observer. Tell me if you have any doubts in this question or everything is all right, so that we can move forward to the next part. And we are almost let's say 80% done with this syllabus of polarization. Few things are left. The phenomena of birefraction or double refraction. We have previously in the initial slides we have mentioned that we have birefraction or birefringence. So that is what we need to talk about. Okay, this is a little bit theoretical, but you will understand eventually. No such big issue. Simple thing. Look, the phenomena of birefraction or double refraction. When an unpolarized light beam is incident, so here we have both perpendicular and parallel components. Unpolarized light normally incident on the calcite. This calcite is a bi-refracting crystal. So when this unpolarized light beam is incident on normally on the calcite crystal, it would in general split up into two linearly polarized beam. One is this, you can see the perpendicular component it contains, another one is the plane component. The beam which travels undeviated. So what do you expect if light ray is incident normally? It goes undeviated, right? That is a normal thing. So one ray is going undeviated as usual. That is known as the ordinary ray, and abbreviated is the O ray. Another and this O ray obeys Snell's law of refraction. Snell's law, you know, n1 sin theta 1 is equals to n2 sin theta 2. So this ordinary ray, it is like it is like as usual. That is following the Snell's law. But on the other hand, we get an additional ray, second beam we get, and this beam is termed as E ray, and this beam does not follow or obey Snell's law, and it is known as extraordinary ray. This 2 ray will only get if you use a crystal like calcite. If instead of calcite, if you had, let's say, glass, if it had only glass, what would happen? This unpolarized light would go undeviated. Okay? It will remain as unpolarized. Recording videos are in Hindi language. We could not understand the theory part. Yes, Murli, we'll repeat those topic. Okay, the recorded video has been provided to you for the time being, but we'll repeat those topics in English as well in the class itself. Okay, so don't worry. So we get two rays, one is E ray, another one is O ray. If we rotate the crystal about Nn prime, the E ray will rotate about Nn prime. So there will be no change in O ray. This E ray will rotate. You can see if you rotate this crystal, this E ray will rotate about Nn prime. Now the appearance of two beams is due to the phenomena of double refraction or bi-refraction. In normal crystal like glass, there is one refractive index N1, but in case of crystal bi-refracting crystal like calcite, there will be two index of refractions. And crystals such as calcite is usually referred to as double refracting crystal. If you put a polaroid PP prime behind the calcite crystal and rotate the polaroid about Nn prime, if you rotate this polaroid, what will happen? Then for two positions of the polaroid, when the pass axis is perpendicular to the plane, so you can imagine when the pass axis is perpendicular to the plane means it is like this, perpendicular to the plane. So if it is perpendicular to the plane, you can see it is making an angle 90 degree, so it will be completely blocked. So when the pass axis is perpendicular to the plane of the paper, the E ray will be completely blocked and only O ray will pass. So you can imagine it, E ray is oscillating in this way and O ray is oscillating along this direction. So if you make this polarizer perpendicular to the plane, it will become like this. So it is 90 degree with this. So this E ray will be completely blocked for this position. On the other hand, when the pass axis of the polaroid is in plane of the paper, line PP prime, so you can see this N, this is oscillating along these directions. If you make it like this, this is blocked. When the pass axis of the polaroid is in the plane of the paper, that is along the line PP prime, then O ray will be completely blocked and only the E ray will pass through. And if you rotate the crystal, this E ray will rotate about this axis Nn prime. Is it clear till now, Murli, Harry? This E ray and O ray. O ray is the ordinary ray which we see generally. If you send some light through the glass, that is that light is O ray. For doubly refracting crystal, we are just getting an additional ray which is not following Snell's law. This is the overall picture. Velocity of the ordinary ray is the same in all directions. The velocity of the extraordinary ray is different in different directions. A substance such as calcite or quartz which exhibit different properties in different directions, they are called anisotropic substance. Glass is an isotropic substance, but you can see the crystal like calcite or quartz, they are called anisotropic because the behavior is not uniform in all directions for the E ray. So along a particular direction which is fixed in the crystal, the two velocities are equal. Okay, that is known as the optic axis of the crystal. Along the optic axis of the crystal, both E ray and O ray will have the same velocity. So in a crystal such as glass calcite, the two rays have the same speed only along one direction, which is the optic axis. Such crystal is known as uniaxial crystal. The velocities of the ordinary and extraordinary rays are given by this. So this V is normal V, V ordinary ray, C by N naught, we know it already. For extraordinary ray, ray ordinary, ray extraordinary, the relation goes like this: 1 by V ray extraordinary square is equals to sin square theta by C by Ne. Ne is the refractive index corresponding to the E ray, and No is the refractive index corresponding to the O ray. So this formula will be used to calculate the velocity of the extraordinary ray. As I told you, N0, Ne are refractive index for O ray and E ray. Theta is the angle that the ray makes with the optic axis. So here in this figure, optic axis has been taken along the Z axis. So C by N0 and C by Ne are the velocities of the extraordinary ray when it propagates parallel and perpendicular to the optic axis. Look, extraordinary ray, it is following this velocity expression. So when it is propagating along parallel direction, parallel to Z axis, so what is the value of theta? The value of theta will be 0. Value of theta is 0, means sin 0 is 0. So this term vanishes, only this term remains cos square. So 1 by C by N0 whole square. So VR is equals to C by N0. That is why it is C by N0 is the velocity when the extraordinary ray is passing parallel to the optic axis. What about when it is passing perpendicular to the axis, means along this axis? So theta will become 90 degree. If theta becomes 90 degree, cos 90 is 0. So this term will vanish and you will have C by Ne. So C by Ne is the velocity of the extraordinary ray when it propagates along the perpendicular direction to the optic axis. Simple, just you need to remember this formula. Calcite is a negative crystal, and as you can see, the ellipsoid of revolution which corresponding to the E ray lies outside the sphere. Sphere corresponds to the O ray which is uniform in along all direction. So this O ray is represented by a sphere. So in a negative crystal, ellipsoid of revolution lies outside the sphere, and in a positive crystal, the ellipsoid of revolution lies inside the crystal. Look, this ellipse represents the E ray. So here we can say the E ray will run faster than O ray. Here sphere is outside, it means O ray will run faster than E ray. So for negative crystal, what you will have? Look, V is equals to, we know, C by N. So N is proportional to 1 by V. More the refractive index, velocity will be less. So E ray will run faster than O ray. It means the refractive index of O ray will be more than the refractive index of E ray here for negative crystal. For positive crystal, what will happen? O ray is running faster, so refractive index of E ray will be greater than the refractive index of is this clear or not? So this sorry, what happens to my throat? Okay, so based on this positive and negative crystal, means bi-refracting crystals, we define retardation plates. We define retardation plates. Retardation plates, we have quarter and half wave plates. Now, if I take the case of the negative crystal, such as calcite, what happens? We know that E ray moves faster than O ray. We can get it from the ellipsoid of revolution. So it is outside, means it is more. Here the sphere is outside, means O ray is more. E ray moves faster than O ray, so that NO is greater than NE. So if D is the thickness of the plate, so it is like you have taken a calcite crystal of thickness D. So if D is the thickness of the plate, the path difference between the two waves on emergence each. So you can imagine it in this way: you have sent an unpolarized light and you get this O ray and you got E ray. So here delta is equals to, it will be how much? You know it, optical path difference is equals to geometrical path difference into refractive index. So here both of them are having refractive index. So you can say N0 minus NE times thickness. Now if you want to make it to be a quarter wave plate, what you have to do? For this plate to be a quarter wave plate, so quarter wave plate means lambda by 4 wave plate. Delta should be equals to lambda by 4. That means N0 minus NE times T will be equals to lambda by 4. That means your T is equals to lambda by 4 times N0 minus NE. So this is for the plate to be a quarter wave plate. Now for the plate to be a half wave plate, lambda by 2 wave plate, delta will be equals to lambda by 2. So N0 minus NE times T is equals to lambda by 2. So in that case the thickness should be equals to lambda by 2 times N0 minus NE. So these are all for negative crystal. Now the same thing will change if I take, let's say, for positive crystal. For example, quartz. Calcite is a negative crystal, quartz is a positive crystal. Here you see O ray moves faster than E ray. So here you will get NE is greater than NO, and delta will be NE minus NO into T, and as a result for a quarter half plate, quarter half wave plate, quarter half क्या होता है, quarter wave plate, the thickness formula will be lambda upon 2 times NE minus N0. Can you write it? Sorry, 4 times. And that the same for a half wave plate. T will be lambda by 2 times NE minus N0. Now what is the job of these quarter wave plate and half wave plates? That is important. Based on that you will be able to apply them. Look, first of all, the quarter wave plate, what it does. Lambda by 4 plate. Lambda by 4 is the wave, part difference. Quarter wave plate. What it does, it introduces a 90-degree phase shift. Why 90-degree phase shift? You can easily understand this. Why 90-degree phase shift? You see, delta, if it is lambda by 4, this is a path difference. Now, from path difference, you can calculate phase difference. What is the phase difference? Delta is equals to 2 pi by lambda into path difference. 2 pi by lambda, lambda by 4, pi by 2. So that is why a lambda by 4 plate introduce a path difference or phase difference of pi by 2. On the other hand, the lambda by 2 plate, this is the half wave plate, introduces a 180-degree phase shift. So here you can say delta is equals to lambda by 2. So this delta is equals to 2 pi by lambda into lambda by 2, that is pi. Okay. Now I have already told you how to check left circularly polarized and how to check right circularly polarized. We have already told you in one of the problems. So first of all, you test it at t equals to 0 and keeping kz is equals to 0. Then you check it at, let's say, t is equals to 0, kz is equals to pi by 2. Or you can do the reverse thing. Okay, we have already talked about it, so not giving you this. You understand, na? Left circularly polarized and right circularly polarized. Okay, let's go to that slide. Yeah, yes, this is what we would have done to check left circularly polarized and right circular. First of all, you will put z equals to 0. Then you will check at some initial time omega t is equals to 0 and some later time, maybe pi by 2 omega. So you can check it whether it is left circularly polarized, or if it is moving along this direction, it is left circularly polarized. If it is moving along this direction, it is right circularly polarized. Okay. Now what is the job of this lambda by 4 plate and lambda by 2 plates? Lambda by 4 plate does several jobs. Lambda by 4 plate, what it does basically, it transforms plane polarized light to elliptically polarized light. It can also convert plane polarized light to circularly polarized light. Obviously these two are very similar. It's about the amplitude only. Too many ads comes. I have to switch off the ad. Okay, it can also convert, let's say, elliptically polarized light to plane polarized light. It can convert circularly polarized light to plane polarized light. This is the job of lambda by 4 plate. On the other hand, lambda by 2 plate, what it does, so very important, it transforms left circularly polarized light to right circularly polarized light. So it is basically used to change the orientation. Left elliptically polarized light to right elliptically polarized light. So you can imagine it in one example like this. So you have, let's say this is your left elliptically polarized light. If you pass it through a lambda by 2 plate, it will become a right elliptically polarized light. And vice versa, yes. So one problem I'm giving you, I think you will be able to do it. A left circularly polarized light beam of wavelength 600 nanometer is incident on a crystal of thickness d and propagates perpendicular to its optic axis. The ordinary and the extraordinary refractive indices of the crystal are n0 equals to 1.54 and 1.55 respectively. The emergent light will be right circularly polarized if d is. Left circularly polarized light to right circularly polarized. If you want to convert it, what plate you need? You need a lambda by 2 plate. Okay. So d we know, and ordinary and extraordinary refractive index n0 and ne. So as you can see, ne is greater than no. What does it mean? For ne greater than no, it is a positive crystal, right? Positive crystal. So d is equals to lambda by 2 times ne minus no. This formula. 600 nanometer by 2 times 1.55 minus 1.54. This will come out to be 30 micron. Clear? Last one question. A plane wave x plus I cap iy cap is equals in e0 exponential I k z minus omega t after passing through an optical element emerges as this. The optical element is. So what has happened in that? We had e naught exponential I k z minus, this is a constant thing, we can keep it. Here it is same. You can see previously it was x plus iy, to it becomes x minus iy. Initially, what we had, e naught x cap e to the power I az minus omega t plus y cap, we can write it e to the power I kz minus omega t. Look, I is multiplied na, I y cap. So I we have not written, so I we can write it as e to the power I pi by 2. Can you write it? We can write it. I is equals to the power I pi by 2. So this is E naught x cap e to the power I kz minus omega t plus y cap e to the power I kz minus omega t plus pi by 2. E final, if you talk about, it is x minus iy cap. So we are writing it in this way, x e to the power I kz minus omega t. Here minus we have, so instead of I pi by 2, if you want to write it minus I, so e to the power I 3 pi by 2, if we do, we get minus I. We have done it in complex analysis, right? So this is plus y cap e to the power I kz minus omega t plus 3 pi by 2. So from this we can say that what is the phase difference introduced. Here it was pi by 2, here it is 3 pi by 2. So pi by 2 to 3 pi by 2. So 2 pi by 2 has been introduced, so there is pi. Phase difference introduced by the optical element is how much? 2 times pi by 2, no? 3 pi by 2 minus pi by 2 is 2 pi by 2, that is pi. Now which optical element introduces a phase shift of pi? We have seen it now. Which optical element introduces a phase shift of pi? It is lambda by 2 plate, which introduces a 180 degree phase shift. So this is a half wave plate. Is it clear, guys? If you have any more question, you can ask, or you can also ask me on the WhatsApp for any doubts, query. We have to switch off this session immediately. So we are stopping the session here, guys. Thank you very much. We're already very late, and have a great day. Bye bye. Take care.